I want to look at is a relatively short unit addressing distribution systems and corrosion control. So just thinking back at what we've looked at, let's just look at this with a surface water system. So we have a surface water system. We have screens. Following screens, the water then flows into what unit? What's the next unit that is most likely to be present in the water treatment system? We have a rapid mix basin. We add the coagulant here. So then we go into flocculation. After flocculation, we have sedimentation. After sedimentation, filtration, and then disinfection. As a water treatment plant operator or as the engineer designing a system, are you finished at this point in time? Okay, we still need to get the water to the people. So we need some sort of storage. We need pump. Pump may be before the storage, depending on how you design the storage. Okay, typically here we will add fluoride. Why do we add fluoride? Really dental health. And we will also add some form of phosphate. And that phosphate is for corrosion control. In Flint, they did not add phosphate or any sort of corrosion inhibitor during the treatment when they were treating Flint River water, but there were actually a lot of other things that they didn't do and that wasn't operating properly in the Flint water treatment besides just the corrosion control. So we need to think about not only the treatment plant, but we need to think about this entire distribution system. So the job of the engineer and the job of the operator is not done at this point here. We need to make sure that the water that reaches the home meets all of the regulatory criteria so that that water, and we use the word safe, but it is as safe as possible. It meets all the regulatory criteria. So we have a distribution system that consists of transmission mains. Those are the largest of the mains. Off of that is a distribution main. And then this will then transport water into the individual communities. So you've got your service main, and then you have the service line. And that is the pipe that takes water from the water main at the street to the home. This is typically the public side. So what's shown in blue is typically the responsibility of the water system. In the US, for the most part, this service line here from the curb stop, and that's where the shutoff is, to the home is typically privately owned by the property owner. That's not true in every location. In fact, in the city of Lansing, they realized that they had a number of lead service lines, and this is back about 5 years ago. They decided that it made sense to start removing those lead service lines. And this was actually mandated as part of the lead and copper rule back in 1991, or it was aimed that this would happen. They sought to do it. Madison, Wisconsin also did the same, but what they did in Lansing was they actually took control of that private line by eminent domain. So essentially, they claimed ownership of this entire area here, which allowed them to go in and do a complete lead service line replacement if that were necessary. And now with the new lead and copper rule in Michigan, it's going to be a lot of work dealing with the fact that now in the state, we're mandated to remove those lead service lines. So I wanted to talk a little bit about the different pipe materials that we use in water systems. And it varies significantly based on location. It also varies significantly based on size. In Flint, much of the old water mains were cast iron, and you'll see that in many locations. These are inexpensive, they're durable. They're being replaced now with ductile iron. It has a higher strength, it's more resistant to internal corrosion, and these are available typically or used typically for water mains up to about 15 inches. These are available up to 64 inches, but typically you'll see these for water distribution systems up to about 15 inches. Copper tubing is what has been used predominantly for consumer plumbing. You will find service lines that are copper. You'll find premise plumbing that is also copper. You will also find both consumer plumbing and distribution systems made of high-density polyethylene. These are not very rigid. They have thick walls, but they are corrosion resistant and durable. There are also a number of other types of materials. Polypropylene, again, this is used for consumer plumbing. Chlorinated PVC polyvinyl chloride here. Okay. These are, again, corrosion resistant, they're durable, they're lightweight. We also, for very large mains, will use reinforced concrete. And up to about the 1940s, we used lead service lines. The lead service lines were actually promoted by the lead industry, by the plumbing industry. They liked lead. It was malleable. It was easy to install lead. It bent easy. You didn't need to use any special equipment. You just simply bent it. And it didn't corrode as rapidly as cast iron. On the other hand, when it does corrode, it results in the release of lead into the water. Now, we want to make sure that when we're distributing water, we need to ensure that it is at a minimum pressure of 20 psi. And that is at ground level at all points in the distribution system. Why? Why do we need to ensure that the system is under pressure?
If there's not enough pressure, it'd be hard for the residents to actually be able to use it, or whoever's using it.
Okay, one reason is just for ease of use. Nobody wants to take, wake up in the morning, take a shower, and then have the water just dribble out. Okay, so we want pressure for that. Why else do we want pressure? So we have here's our ground surface. We have a pipe underground. Why do we want the water flowing under pressure in this pipe?
Does the earth pressure have to do with it?
Prevent backflow?
Sort of. What don't we want happening? If we have a leak in the pipe, which way do you want water flowing?
You want water flowing out of the pipe.
Exactly. Okay, why do we want water flowing out of the pipe?
You don't want to get contaminants. Yeah.
Exactly. We want to prevent infiltration and contamination. In fact, if you have a water main break, which means you lose pressure in your piping system, then you need to be able to shut off water, isolate that pipe, fix the leak, and then you hyperchlorinate to try and make sure that you're killing any organisms that have infiltrated into that piping system while it was depressurized. So you want a minimum pressure of 20 psi. Normal working pressure is about 60 to 80 psi. Ideally, you don't want less than 35, but that minimum pressure is 20 psi. Just give you some sense in terms of sizes of pipes. That water main, looking back here, so we're looking at this water main here. If you're providing fire protection, which in many cases communities are, so anywhere you see fire hydrants, they're using the water from the distribution system to provide fire protection. In that case, the minimum diameter of your water main is 6 inches. And that's because during a fire, you need to be able to pump large volumes of water very quickly. If you're not providing fire protection, then 3 inches is the minimum diameter. The other thing you want to do is you want to minimize dead ends. So what does that mean? We talk about a dead end in the system. So let's think Ide Boulevard. And you've got lodges here, you've got a road, you've got lodges phase 2 here. Okay. And you have a distribution system. What we don't want in the distribution system is this to be a dead end. Okay, this to be the end, basically the end of the distribution system. So what we want to be able for water to flow, for instance, in this direction, then in this direction, and then I forget the name of the road, this way, and water can flow in this direction. So water is flowing and it's not stagnating. Ideally, you want a minimal number of dead ends, because in that situation, you're essentially at the end of the pipe, water is going to tend to stagnate. And if water tends to stagnate, then it's sitting there. It's more likely to have chemicals from your pipes dissolving into it, bacterial regrowth in that system, and degrading the quality of the water. So you, as you're designing your distribution systems, you'll look at this in 422, if you haven't already. When you're looking at designing your distribution system, you want to make sure that you have as few dead ends as possible. It also allows you to have increased reliability. So if if this is a dead end and water flows only in this direction, and I have a water main break here, and if I don't have a way to redistribute water, then nobody in this area is able to get water. So if I have valve, and this is why I need valves in the system, if I have a water main break here and I can adjust the valves so that now water flows in this direction, I can provide all these apartments in Lodge's Phase 1 with water. So as you want to ensure that you have as much flexibility as possible in your distribution system. So you'll have valves that are located at intervals of not more than 500 feet or 1 block in residential areas. In the commercial, the reason is just you need typically more water usage. So you want to be able to shut off and isolate those regions if there is a water main break. So there's different types of valves. Selection depends on what you're trying to achieve and issues like head loss. And I'm just going to show you a few different types of valves. So this is a gate valve here. And so see here, okay. It has a flat or a cylindrical or a spherical surface that slides across an opening. So water would normally, if this is up, then water flows through. If it's screwed down, then you have no flow. This is a globe valve, and a globe valve has a disc or a plug that moves into an opening. So this moves up or down, and you can see the plug right here that actually closes flow. And you can see if it's open, water's flowing in this direction. If it's closed, it shuts off flow. And this is what a globe valve would look like. This is a diaphragm valve, and it has a diaphragm. It's typically what you'd have on a faucet, and that opens and closes, and it can either be completely closed or it can be partially closed to restrict flow, which is what you normally do on a faucet. And this is a butterfly valve, and you can see this opens or closes, flips back and forth that way. It's just to give you a sense of the different types of valves. In the virtual tour of the MSU system, you'll see a number of types of valves, and I'll ask Tom to point out some of those valves in the system. We also have specialized valves. We have check valves, pressure relief valves. There's one shown here. Often, if you want that 80 psi, but you don't want water delivered at 80 psi, you have a pressure release valve in the system. You may have a pressure release valve at the home. You also have backflow preventers. You don't want water flowing back into the distribution system. So for example, if you were to look at the plumbing in those of you actually in an apartment or in a home, you have a backwash backflow preventer to ensure, for instance, that water from the kitchen drain doesn't flow back into the distribution system and then recycle around, and basically you're drinking your drain water. Not a good thing. We also typically provide storage, and we use the term tank and reservoir essentially interchangeably. We can have ground level tanks, and that is simply a tank on the ground. Those of you that have done the scavenger hunt, did you find a ground level tank? Or where did you find the ground level tank? Who's doing the scavenger hunt? Okay, didn't locate it. It's right next to Impression 5. You can see it from their parking lot. You can see it from the river trail. You should be able to see it. In fact, I know you can see it from Google satellite view. Okay. There are 2 ground level tanks at the John Dye water treatment plant. So if you haven't looked at those, okay, there are 2 that you can look at there. You can also have elevated storage. MSU just built an elevated storage tank. You can have pump storage. This is below the hydraulic grade line, and pumping is required. MSU used to have pump storage just west of the engineering building. Anybody ever notice the mound? There's a building, just a small little building next to the parking lot, and to the south of that is the urban planning landscape architecture building. Anybody notice that mound that is kind of in that area right there? So here's the engineering building. This is Red Cedar. The parking lot is here, commonly known as the dirt lot for those of us that have been there for a long time, because it was dirt a few decades ago. When I started, it was dirt. This building here was the water treatment plant. Urban planning landscape architecture is right there. Behind here, there was a large mound. Under here was a 1 million gallon storage tank. Few people knew about it, but there, and that would be pumped storage. And the last thing we talk about is clear well storage. And there we've gone from filtration. Typically we have at the plant some sort of storage. This is often below ground. In Flint, this was a 3 million gallon tank. This is used for contact disinfection or disinfectant contacting often. So it provides storage, but it also provides volume and detention for disinfection contacting. So we'll stop there. And so we will meet tomorrow at 10:30. Okay. And our guest speaker, as I mentioned, will be Tom Silsby from the MSU water treatment plan. And it would be beneficial if you watch the short 13-minute or so lecture that I put together on arsenic, iron, and manganese removal before that meeting. So happy to answer any questions that anybody may have.